Hello, community. Today, something really interesting. Self-RAG. So, self-reflective retrieval-augmented generation. And of course, you know what is self-reflection now in the human context, to examine one's own thoughts, the feelings, and action to gain a deeper understanding. And from psychology, we know it helps individuals to recognize their thought patterns. But if we use this in computer science, things get much more interesting. So we have AI systems that monitor their own behavior, reassess their strategies, and adapt new circumstances in a multi-AI agent environment. And I can tell you, it is a fascinating idea. So let's dive right in. So our self-RAG framework aims to enhance the capability of our LLMs by integrating the retrieval and self-critique mechanism into the model's generation process. So what does this mean? Now, normally we have here our AI system, a beautiful little LLM, a Llama 2 model, a Mistral model, whatever you have at GPT-4. And then we have data, external data. Data somewhere in your company external database, and you have SQL, or you buy somewhere an external vector store, or you're looking for internet documents, and you notice this is the classical RAG. So we are talking about RAG-based database APIs or RAG-based vector store API. Great. So give you a simple example. I have a question how to make ice cream. And now let's assume that here the vector store here, the vector space that was generated here, is in a non-coherent fashion here with our LLM. So we get an answer, hey, ice cream in a topological paradigm is a space-time event cluster that represents a quantized equilibrium state with a Riemann-flavored manifold. And each scoop is a distinct vector in this manifold. So you see, the answer our LLM gets back is integrated if it makes sense or not. And we rely here primarily here on those external databases or vector stores here on an intelligent query mechanism. But we have no control over this, and you see when it's integrated, it's maybe some nonsensical data. So this normal RAG we want to overcome, we want to improve by integrating here the retrieval and the self-critique mechanism. So let's have a look at this. We retrieve text segments from multiple parallel external sources. Great. And then the idea is simply to use a filter. To use a filter to evaluate the semantic relevance of the extracted text segments we get back from the databases, we get back from the vector stores, given our original query. So what we do? We let an AI system evaluate those return segments and says, number 1, yes, number 3, yes, number 2, fails. So we have here a simple filter, you see, not complicated at all. Now with those received text segments that are allowed and passed through the filter, our AI generates now multiple responses, parallel responses, given segment number 1, given segment number 3. With those retrieved, we have multiple responses, and now it's easy. The AI evaluates now each response with this retrieved information from a particular external data source. That's all there is to it. And how it does this, the AI criticizes its own output based on the factor of the factuality and the quality, and then chooses the best AI-generated response from the set of parallel generated AI responses. You see? And we will use here a token. No, not an NFT token, but we will use here a classical token. Remember, we are here with LLM, so we have here a token-based structure. So we will use here now that we have here the word tokens or the subword tokens or any other configuration of tokens, and we will add some tokens to our vocabulary of our LLM. And we will add 4 different kind of token. If the AI decides now, answering here my query, that it needs access, it will have here a very specific token, a retrieval token. And the AI will decide when is the time to go and activate a retrieval token. Now, if the messages come back, you see here we have a filter. This filter here is a critic token, and we have 3 critic token and an evaluation. So the first one is simply giving us, hey, the answer we receive back is relevant or not. It's a simple yes or no, a go or no-go decision. Then, with the answer that passes through the filter, we generate here, or the AI generates responses, multiple responses in parallel, and those responses are evaluated too. Now the first, and we have here 2 decision tokens. The first critic token here criticizes the output of the AI. So it self-reflects on the generated output, given if the actual information is factually correct or not, and about the quality. And then, having information about this, it ranks all the different responses and chooses here the best generated response, simple by schema 1 to 5. This is it. Now you know the theory of self-RAG framework. This is all there is to it. If you want to have here now the view from the preprint, look, we have here our 4 reflection token, we have 1 retrieval token, and we have here 3 critic token. And as you can see here now, our output here, what values can the token become? Easy. If you retrieve it, is a go or a no-go decision. Yes, I should retrieve something. No, I should not. Or I could just continue. Second is the information I retrieve from external vector store relevant to the task or not? So I have relevant or irrelevant as my status, as my state. Then we have, is the information that is coming back fully supported, just partially supported, or not at all as support to my task? And then we have the quality token, if you want, is useful token, where we have 5 to 1, so we have a numerical valuation scheme. This is all there is to it. Now, if you noticed, and now I come to my ideas, this is here on a linear action chain. If you want to integrate now graph neural networks, and please, this is not in the study, this is just my idea that I get when I read those papers, we can have now going from a linear data structure to a graph data structure, and we can apply here the instrument of graph neural network for information retrieval. So our GNN could encode more complex relationship between the document and the retrieval phase, another layer of sophistication. Because imagine if you have here on the edges here decision markers or decision tokens or reflection tokens, you will find very different paths here in an n-dimensional graph network. But this is just an outlook for my next videos. So, for Ben, in some simple words, self-RAG first determines if augmenting the continued generation with retrieved passages is helpful. If so, it outputs a retrieval token that calls a retrieval model on demand. So the AI generates here a retrieval token and says, hey, I need more information from the outside world. Self-RAG concurrently processes multiple received passages, evaluating their relevance, and then generating correspondent task outputs, AI responses. If it then generates critique tokens, we have 3 critique tokens, to criticize its own output and chooses the best one in terms of factuality and the overall quality. So you see, self-RAG provides citations also for each segment with its self-assessment of whether the output is supported by the passage, leading to an easier fact verification. This is nice, Ben. Why we have self-RAG? Here is simply we tackle 2 core problems with our LLMs. At first, they are factual, maybe incorrect, due to limited, and here we look at vector stores, parametrically encapsulated knowledge that the vector space is incoherent and. And second, we have here in the classical RAG system an indiscriminate retrieval of passages in our RAG models, which may compromise the versatility of the model and introduce irrelevant or inaccurate information I showed you with my ice cream and the Hilbert space. So we want to get rid of this. And this is why we have self-reg. We have this in the context of multi-agent system, or if you look at the pure AI system, of self-adaptive system. And if you say, hey, I know this critic model somewhere, yes, of course, it appears that this critic model is a function similar to our reward model, offering a way to guide the learning process. Remember, reinforcement learning by human feedback, PPO, DPO. This here is something else, but something cleverly integrated. Of course, if you have a model that has already been optimized with a reinforcement learning by human feedback, then you have to be particularly careful if you apply now a critique training process on this data. I will show you the details in a minute. So here we go. Just to give you a feeling, what are our training examples? Those are LLMs. We have two LLMs we have here. We have the text generating model and we have the critique LLM. So how do we train those? Now, it is easy. We have an input. When did Walking Dead Season 7 came out? This is here the query. We ask, for example, Llama 2 or ChatGPT or whatever you have. And then the system says, okay, do I need external information? Retrieve equal yes. This is what the AI decides. And this is the time that the AI decides, hey, I need help. So then we retrieve something from somewhere here. We then judge, hey, is this information we just retrieved from a specific API that we have here as a primary context to, is it relevant or irrelevant? If it is relevant, great. We then have here the extraction of the information. This is a date. Now the AI system says, hey, is this the date that answers here really exactly the task I'm given? And yes, it is fully supported. This information fully supports the capability to answer this. And if you want the quality, since we solve here is the highest level 5. You have this, of course, also with task where you have no retrieval. If the task to an AI system is, hey, synthesize a poem based on this prompt, then you know GPT-4, for example, does not need any external factual information. It has enough information in itself to create a poem. So you see, retrieve is no, retrieve is no, retrieve is no. So whenever a sequence or a sentence ends, here we give the model into training phase. We show him, hey, check if you need to retrieve more information. If not, just do the job without any external data. Now, if, for example, you have a little bit more complicated task, read this, you see GPT-4, for example, comes back, has some information, then decides itself, hey, I need more information, gets there to a vector store, gets some information, says, hey, this information is relevant. You have a multiple stream of information coming in. You use this information to generate here the next tokens in your generation of text. Yes, yes, yes. Then you say, hey, is this here supported, the information, for my continued text generation? Yes, partially here. Okay. Why partially? We are talking here about the dog, and the dog here is giving that they are more or less working for the police work. And you see here what GPT comes back with in its generation says, these dogs are often used for disability assistance and for police work. Now, since here the paragraph text only focuses on police work, the disability assistance is not met in the information we extracted from the external environment. Therefore, we only have a partially supported information base. And the question, is it useful? Since we only have here partially supported, the AI says, hey, this is 2 in our training dataset. And yes, you guessed it, those training datasets are generated by GPT-4, or in the future, our best general AI system that we have. If you now go for a really complex system with a multitude here of self-evaluation, reflection, this is an example situation where you have to delegate some task. At first it says, GPT-4 decides, hey, I just go with the first sentence. So retrieve no. Manager realizes there's an extensive list of tasks needs to be completed in order to make an event a success. Then AI says, hey, now I need some information. Judges here with here a critique token. This is relevant information. It builds now the next response, says, hey, this information was partially supported. Can I go on? Yes or no? Says, yes, I can go on. Okay. Then comes to the point where it needs another information, and this goes on. So you see, this here are synthetic training data created for the system to learn when to use this system. And I made here an experiment. I took this and I trained, for example, on GPT-4 here for a very limited amount here, those tokens, and I asked the system to evaluate the function of the token, and it came back with some perfect answer. So what is the performance of all of this? Is this working? And the authors here of this algorithm tell us here, if you look at the last two lines, yes, beautiful, almost outperforms any other Llama 2 model, the Llama 2 7B, the Llama 2 13B model. If we apply self-reg to a Llama 2 model, it outperforms the classical Llama model. Great. Now, if you want to have a deep dive into the publication, here it is. And as you can see, Washington, University of Washington, Allen Institute of AI, and IBM Research AI. Really nice paper, new, fresh ideas. If you want to go into RAG and have here for the multi-AI agent environment, this is the paper for you. If we have some mathematical beauty, if you want to be precise, we look at the pseudocode, and I will show you how we code it in a minute. So here we go. A self-reg inference now. Here it is in pseudocode, and here you see it written out. So let's go this step by step. So as I told you, we have a language model, a generator, we call it M, and a retriever or a database. And then we have a large-scale passage collection from external retrieved data from D. I don't know why D, deeply retrieved data or whatever, D. So here we go, input. We have an input prompt to an AI, to GPT-4. This is my prompt. I ask GPT a question, X. And the preceding generation, Y by GPT-4, smaller than T. And given that we start, we have here nothing, but given we already have something, we have here already some history in our conversation. And then the output is the next output segment, Y, at the time T. And now happens two things. The model now predicts, do I need external data? Should I have my retrieve token active or passive? If it says yes, then we do this. If it says no, I don't need to retrieve anything, then the model just generates here the next token, You know, we have an autoregressive LLM. So our next tokens are determined by the model given our task to the system. And then our system predicts here, if you want, the quality parameter of whatever has been generated and takes the best one. Now, the interesting part, of course, is if we have here that the system decides, hey, I need some external additional information, augmented information from external sources. So we retrieve the relevant text passages, D for deep dive, using here our retriever, database, whatever you have given. We have here a pair of my input X, my query input, and the response by the AI at a time interval t-1, so the historic time interval just before today, just right now. So then M predicts if this is relevant given my data of my query, my retrieved information, and the generated next token sequence by my AI. Then it predicts, is it supportive, yes or no? Since is relevant is my filter I showed you. Now we go, is it relevant, yes or not? And then we have simply the quality. This is it. But you know, the pseudocode is not that precise. So let's switch for a moment here to the text that I shortened up for you from the original publication. So what we do. For every x and preceding generation y, the model decodes a retrieval token to evaluate the utility of the retrieval. This is our retrieval token. If it is not required, the model goes on and predicts the next output segment, the next tokens, the next part of the sentences, as it does in a standard language model. If a retrieval is needed, the model generates. And now, please watch out. We have 3 tokens. A critic token, C1 if you want, to evaluate the retrieved passage relevance, so the data from the vector store, plus the next response segment as generated by the AI system, and a critic token C2 to evaluate if the information in the newly created response segment of the AI is supported by the passage extracted from the vector database. So if this information, as I showed you in the training example, is supported or partially supported, it passes. And then we have a new critic token C3 that now evaluates the overall quality, the utility of the response. And this is it. So we have 1 retrieve token and 3 critic token with very specific task. And if you think of it, it makes sense. The retrieve token tells us, hey, is this a go or a no-go for external data? Done. Then we evaluate now the incoming text passage from a vector database. Is it relevant here to the task, the query that I asked the system to do? Is it now in relation to the next response segment that is created by the AI? Here evaluated, and then you evaluate simply the information if the information fits together of the new response segment by the AI and the external text passage as imported from a vector database. And if you have this and you have another go, then you simply go here and rate here, or you rank here the quality, and you take the best quality answer. This is it. As easy as this. So just to give you an overview, the components I already told you. We have an LLM. We call it a generator model. The generator is responsible for the text generation. Great. However, please notice this is not in the training phase our normal LLM. This is an advanced LLM. I will show you in a minute. Then, whatever retriever we have, this just retrieve text, info, strings, sequences of strings from some external vector store, databases, internet, whatever. And then we have the second essential model, an LLM. This here is a Llama 2 model here in the paper, and this also is a Llama 2 model here. A critique model, a second LLM. Now this has a specific task. It generates reflection tokens, C1 to C3, for evaluating the generated text and the retrieved text passages from our vector stores. So you see, we have here, and maybe you think about here reinforcement learning with the reward model, with the policy options. We have now a critique model. Note that the critique model is similar to this reinforcement learning, but has some advantages. Do you guess which? And of course, we have the 4 reflection token in the key components. Special token, as I showed you, retrieve and C1 to C3. Great. Now, interesting is how you train this system with 2 LLMs. So we have to train the critique model and we have to train the generator model, this classical. Now, we call the critique model C and our generator model M for the main model. The critique model, or LLM, is trained on a dataset annotated with reflection tokens to predict the appropriateness of such token in various situations. So here we have an LLM that needs a huge data set with an actual use case of reflection tokens. Not just where the reflection tokens is, when the reflection tokens are, but also the quality of the reflection token. This goes from the utility, from the usefulness, from 5 to 1. This goes to fully supported, partially supported, not supported at all. We need here a huge data set, and you guessed it, GPT-4 is here really helpful. But remember, every problem we have within GPT-4 will be transferred here also to this training data set. It is a synthetic data set for a critique LLM. And then we have here our classical LLM, our classical main generator model, our autoregressive LLM. But hey, careful, watch out. This generator model is now trained with a huge different training data set. And in this training data set, we have millions and hundreds of millions of tokens. Plus, we also have here this specific tokens that we add, and we add here the critics output. So everything that comes out from this system is now integrated in this system, and the generator model is trained with the critique LLM outputs generated, included in its M training corpus. So the generator now learns to produce both the target output, like a normal LLM, and the reflection tokens. And now all 4 reflection tokens. When should a system be able to retrieve external information? It learns this. And given C1 to C3, also here the reflection token for the critique model, where to apply it and when to apply it, when to generate it. Because remember, we are in an autoregressive system. So the tokens are now generated by M. And thereby internalizing here the complete critique process. So here you have it, 2 systems, great. And you see they are really interwoven. And yes, this C data set, as I told you here, reinforcement learning, interesting parallel, but there's still a difference. Okay. Yeah, inference. So we have inference and training. Let's look at inference first. The generator predicts if a retrieval is necessary via a retrieval token set to active. If so, it uses the retriever and the critique model to fetch and evaluate the relevance and the supportiveness of external text passages, and it also then assesses the overall quality, the overall utility of the generated output by the AI system and uses only the best response. Great. Now the training involves training both the critique LLM and the generator LLM. The critique model is trained to predict reflection tokens, while the generator LLM is trained to produce the text as well as those tokens, as I showed you. If you have now, and you ask, hey, but what are our mathematical parameters that we optimize here? In the critique model, let's say it's a Llama 2 model, trained to maximize the likelihood of generating the correct reflection token given input-output pairs. And in the generator model, also a Llama 2 model, for example, is trained using a next token prediction objective, like we know it, like we love it from our classical LLMs, but extended now the generator model to include here all 4 reflection tokens. So whenever our generator LLM produces here as an autoregressive model the next token, maybe it is not a word or a subword token, but maybe it is a reflection token. And this is the new interrupt when the system decides, hey, I need external information, external sources to add to my body of knowledge. Or it says, given that I have my self-reflection ability, which of the critique tokens do I activate and how to evaluate here the value? If you want to have it in a little bit more precise mathematical beautiful form, here we are, critique learning, and this is what we have, and generator learning. Here we train generator by training the correlated corpus augmented with the reflection token using the standard next token objective. So this is what you optimize your system for. Hey, why not? Let's code it. And here we are now coding here self-reg. So at first we have our transformers, our auto-tokenizer, our auto model for causal language model, and then we need VLLM. Now, if you're not familiar with VLLM, it's an efficient memory management system for LLM serving with paged attention. And there are some points where we use it because at first we have here an efficient memory of attention, key, and value memory with paged attention. And we have a continuous batching of incoming requests. This is especially important if we do some rack system here. We have a high throughput. We have tensor parallelism support for distributed inference. We have some streaming outputs. And of course, we are compatible here with Hugging Face models. So this is why we use here in the background. And here we go. Our model, our LLM, is simply from Hugging Face, from self-reg. We have here the Llama 2 7 billion free trainable parameter model. We download it. Great, we have some sample parameters. And now comes the interesting part. Please, this is important, the prompt structure. You need a specific prompt structure. You need to choose the correct format, especially if you have additional input. So you have your format prompt and you have your prompt and you have your normal instruction and response format. But if you want to insert more data, more paragraph, then you have here this exactly format. Please take care about it. So you can insert paragraphs here after here the response field, but make sure to mark the paragraph here as paragraph tokens exactly as shown here in this piece of code. And then you are good to go. Now, let's do here one or two queries. The first one is leave odd one out, Twitter, Instagram, and WhatsApp. And then can you tell me the difference between llamas and alpacas? So let's see here this in action. So we have here our model that we downloaded from Hugging Face. We have here the format prompt here for the first query. And what happens is the model prediction comes back and says, hey, Twitter, Instagram are social media platforms. We have here no retrieval. Then WhatsApp is yes, yes, yes. And we have here the utility, the rating of the quality here with 5. And as you can see, this does not require any factual grounding. This means we do not need any external data for this. Now, in the second model, it is much more interesting because can you tell me the difference between llamas and alpacas? And maybe you are not familiar with this, or the AI system is not familiar. So what you have your format prompt, you have here exactly your question, and then you just input here. Imagine you are a vector database. Just for demonstration purposes, you give here now exactly the external information and additional augmented data for the AI to work with. And you say, alpacas, series, yes, similar to, often, yes, yes, yes. And then you get exactly the answer given here, integrating here this paragraph information. So you see, if you run inference, this is the complete code that you need for experiencing self-reg yourself. Now, as you see here, we have here from self-reg the Llama 2 7B model. But just want to show you, if you go here, Hugging Face self-reg, you see we have two models. We have the Llama 2 7B model and the Llama 2 13B model, updated 3 days ago. So interesting model, have a look at this. But what's of course really interesting is the training data set. Now, self-reg has here one training data set it published here. And it is easy. You have an instruction and an output, and you see where it comes from. This comes here from the FLAN collection. This is here the absolute FLAN identifier. And you have, I don't know, some question. Write something where you have no retrieval. Great. But if you have some retrieval here, for example, you see here we have this paragraph notation. Some external information is read in, but remember we are just in the training phase here. So we say, okay, this is now the information that we get from an external source. Then we judge that this information is irrelevant for the specific task. And we have here the utility given. And you go on and you can have a look here at all the different things where here the training data set show here the system how to learn this. Anything else? No, not really. Maybe what you should have a look at is we go at self-reg, the GitHub. Here we go. So if you want here the archive paper, the code, the two models, and some data, here you have it condensed on one page. Here you have also a summary here from the official paper with some visualization and here the official reference. Beautiful. Now, having read such an interesting paper, maybe you too, you have questions and you say, hey, I'm thinking about possible expansions. I think possible integration. What will be the next step? So why not have a look here in the near future? Where are we? We are here in a dual optimization objective for our LLM. Now this is interesting because we don't have this normally. So our LLM model now optimizes for both the content generation and the content evaluation. This is notably a complex task and poses question regarding here how to optimize here the mathematical computer algorithm here for an optimization in finding here the solution. If you look at it from the information theory side, the idea of reflection token introduces something like a meta layer of information, creating a more complex information theoretical model. And if you go to Shannon, grandfather of IT, those tokens could be seen as extra channels in the communication process between the machine and the human. And this is interesting in itself. But let's jump also to control theory and here our decision-making process. Now, our self-reg adaptiveness, as I told you, the AI system decides when it needs data, and it also qualifies those data and evaluates those data itself. So this adaptiveness to task requirements could be seen through the lens of a control theory approach, where the system adjusts its own control parameters, frequency of retrieval or the quality threshold, to meet certain objectives. So interesting. And of course, we look here at ethical and epistemological consideration. Introducing self-critique and retrieval into models can have broader implications, particularly here in how they select and how they validate external information sources. Because now the AI decides, given your particular query, if the information it extracts from source A, let's say this is Fox, or from information source B, this might be CNN, which is the most successful information retrieved for your query that you say, yes, this is what I thought about it. And this gives you a very interesting perspectives of the future of the validation and the quality of external information sources. But let's look at complex system theory. In this system theory, think about it here as a feedback loop with some non-linear components. These are the interesting components. You have critique and this generator model, and it would be interesting to employ behavior in terms of stability, sensitivity, and adaptiveness in a complex system theory. But of course, those systems all serve here or augment here the human decision-making process. So if we now look here in the relation to the human cognition and human decision-making, I think here the concept of self-critique aligns with this higher order cognitive processes that we have so easy in humans and are so difficult to implement in AI system, where the evaluation and the adjustment are just integral parts here in performing here complex tasks, complex arguing task, multi-step argumentation. But again here, it closes the loop because think about multi-agent AI system. With this information, if the LLM learns in your particular use case to present you information that you like, for example, from Fox or from CNN or from MSNBC, whatever is your information source, this has an effect of a login, of being placed inside your bubble and being reinforced within your bubble. So I think it would be interesting here in the view of a complex system theory to have here a chaotic element. You know, somewhere in the term, somewhere you have a term that says, hey, and now I'm an irregular term. Now I jump out of this system and I go somewhere else and I bring some new ideas into the system. So I think this would be the next evaluation step of this self-recognition RAG, reinforcement augmented retrieval system here in our multi-AI agent environment. Great, I think this is it for today. I hope I provided some food for your thoughts, and it would be great to see you in my next video.